Good day. Today we're going to discuss the elementary matrices and the methods for finding the inverse of A. So, in this discussion, we will develop an algorithm for finding the inverse of a matrix, and we will discuss some of the basic properties of invertible matrices. Now, in the previous discussion that uh, we already defined three elementary raw operations on matrix A. We have multiply a row by a non-zero constant C, and then we have interchange two rows, and then we have add a constant C times one row to another. It should be evident that if we let matrix B be the matrix that results from matrix A by performing one of the operations in this list, then matrix A can be recovered from matrix B by performing the corresponding operation in you have following list. You have multiply the same row by 1 over C. Then we could also have interchanged the same two rows. And then we have if matrix B resulted by adding C times, let's say, row R sub 1 of matrix A to row R sub 2, then add negative C times row or R sub 1 to R sub 2. It follows that if matrix B is obtained from A by performing a sequence of elementary row operations, then there is a second sequence of elementary row operation which, when applied to matrix B, recovers matrix A. Okay, so let's start our discussion with definition 1. Matrices A and B are said to be row equivalent if either, hence each, can be obtained from the another or by other by a sequence of elementary row operations. Okay, now our um, our next goal is to show how matrix multiplication can be used to carry out an elementary row operation. Okay, now in the second definition, we have an n by n matrix is called an elementary matrix if it can be obtained from the n by n identity matrix I sub n by performing a single elementary row operation. Okay, so we have here if the elementary matrix E results from performing a certain row operations on I sub m, okay, I meaning its identity, and if matrix A is a matrix, then the product of EA is the matrix that results when this same row operation is performed on matrix A. Okay, so this is the theorem 1.5.1, which is the row operations by matrix multiplication matrices. So let's have an example. Now you have consider the matrix. You have A with an element of 1 2 1, 0 negative 1 4, 2 3 4, 3 6 0. And then we have also to consider the identity matrix. Okay, so we have that one. Now, if we are going to what we call this one, multiply the uh, third row, okay, of that what we call this one, element, if we're going to uh, 3 times the first row of that identity matrix to uh, multiply 3, then add it to the third row, then we can have the uh, elementary matrix. So for the elementary matrix, again, using the concept that we are going to um, multiply 3 to the first row of this identity matrix, then we are going to add to the third row. So our matrix would be you have 1 0 0, you have 0 1 0, and for the third row would be you have 3 1 0, and this is now the elementary matrix. Now if we are going to have EA, meaning we are going to multiply the elementary matrix to our matrix A, we could have the what we call this one. We could have the resulting matrix of you have 1, then you have here you have 0, then you have 2, then you have 3, then here you have 2, you have -1, here you have um, 3, and then you have 6, then you have 4, 4, um, 10, and 9. We are just going to multiply the elementary matrix to A. Okay. In this case, this is actually the same matrix that results when we add uh, 3 times the first row of the matrix A to the third row. So this is actually the theorem 1.5.1. Okay, this theorem is helpful, okay, and useful for developing new results about matrices. But as a practical matter, it is usually preferable to perform row operations directly. Okay, now, okay, this one. Um, we know from the discussion on the first discussion that we had that the elementary matrix is uh, what we call so that if the elementary matrix that results from performing an elementary row operation on an identity matrix I, then there is a second elementary row operation which when applied to the elementary matrix, it produces the identity back again. So in this slide, it's the list of these operations. The operations on the right side of the table are called the inverse operations of the corresponding operations on the left. So you have, if you have multiply row I by C, which is not 0, then you could have multiplied that row by 1 over c. Now, if you have to interchange row I and j, you have to interchange the row I and j. And then if you have to add c times row I to row j, then you have add negative c times row I to row j. Okay, okay. So let's have an example. Row operations and inverse row operations. Now, in each of the following examples, an elementary row operation is applied to 2 by 2, okay, identity matrix to obtain an elementary matrix A. Then E is restored to the identity matrix by applying the inverse row operation. So for example, you have here a 2 by 2 identity matrix. Now, if we are going to multiply the second row by 7, so if we are going to multiply here 7, then our what to call this one, our elementary matrix would be 1007. Okay, and then if we are going to reverse this one, okay, then you have to multiply the second row by 1 over 7. So you have 1001. Okay, next, if you have the same, okay, and then if you are going to interchange the first and second row, okay, if you are going to interchange the first and second row, then you have, of course, 0110. And then if you are going to reverse it again, you are just going to interchange the first and second row, which you have 1001. Okay, then if you are going to multiply 5 to the second row, then add it to the first, then okay, you have here, you have 1 5 and 01. Then if you're going to revert it again, okay, to the identity matrix, then you are going to multiply negative 5 to the second row, then add it to the first row. So you have 1001. Okay, so let's have theorem 1.5.2. So it states that every elementary matrix is invertible, and the inverse is also an elementary matrix. In other words, if uh, matrix E is an elementary matrix, then matrix E results by performing some row operations on identity. So if we are going to let E sub 0 be the matrix that results when the inverse of its operation is performed on the identity matrix. So from the theorem 1.5.1, and using the fact that inverse row operation cancels the effect of each other, so it follows that you have E sub 0 times E is equal to I. Okay, and if you have E times E sub 0, it's also equal to I. Therefore, the elementary matrix E sub 0 is the inverse of the matrix E. So let's have the equivalence theorem. So one of our objectives as we progress through this discussion is to show how seemingly diverse ideas in linear algebra are related. So the following theorem, which relates results um, we have obtained about invertibility of matrices, homogeneous linear systems, reduced row echelon forms, and elementary matrices, is our first step in that direction. So as we study topics, more statements will be added to this theorem. Okay, so we have here equivalent statements. Okay, so uh, this is equivalent statements. If matrix A is an n by n matrix, then the following statements are equivalent. That is all true or all false. So we have A is invertible, AX is equal to 0 has only one trivial solution. The reduced row echelon form of A is I sub n, and A is expressible as the product of elementary matrices. Okay, so we have a method of for inverting matrices. As a first application of theorem 1.5.3, we will develop a procedure that can be used to tell whether a given matrix is invertible, and so uh, produce its inverse. To derive this algorithm, assume for the moment that matrix A is invertible n by n matrix. So the elementary matrices execute a sequence of row operations that produce um, matrix A to its inverse. Okay, so if we multiply both sides of this equation, okay, on the right by inverse of A and simplify, we can obtain this one. Uh, A is a negative 1, the inverse, which is equal to the elementary matrix K multiplied so often to E sub 2 times E sub 1 times its inverse. Okay, but this equation tells us that the same sequence of row operations that reduces matrix A to its inverse will transform the inverse, okay, to A raised to negative 1. Okay, so to find the inverse of an invertible matrix A, find a sequence of elementary row operations that produces matrix A to the identity, and then perform the same sequence of operations on the identity matrix to obtain the inverse. Okay, so let's have an example. Let's say consider the matrix. So matrix, we have that one, matrix A. Now we want to produce A to the identity matrix by row operations and simultaneously apply these operations to the identity to produce the inverse. So to accomplish this, we will adjoin the identity matrix to the right side of A, thereby producing a partition matrix in the form of you have um, like this one, okay, the identity. Okay, then we will apply row operations to this matrix until the left side is produced to identity. These operations will convert the right side to the inverse of A. So the final matrix will have the form of uh, you have something like this. Okay, so the identity matrix, and then on the right side is the inverse. Okay, so in this case, okay, since we have this one, then here. So take note that you have uh, let me check first the entries. So you have something like this. You have 1 2 1 2 5 0 3 3 8, and then you have the bar, and then the identity, 3 by 3 identity. So 1 0 0 0 1 0, and then you have 0 0 1. Okay, now in this case, we have to multiply -2 to the first row, -2 to the first row, then we have to add it to the second row. And you have -1 times the first row to the third. Okay, so again, we have you have -2 times the first row, then add it to the second, and you have -1 times the first row, then add it to the third row. Okay, so in that case, we have the resulting matrix of you have 0, not 0, this should be 1. You have 1, 2 3, and then you have 1 0 0. Then you have here uh, 0 1 -3. Then here you have -2 1 0. Then here you have 2, no, this is 0, then -2 5, -1 0 1. Okay, now in this case, we have to multiply 2 to the second row, then add it to the third row. Again, we have to multiply 2 to the second row, then add it to the third row. So here we have you have uh, 1 2 3, then you have 1 0 0. Then here you have 0 1 negative 3. You have negative 2 1 0. Then here you have 0 0 negative 1. Then you have negative 5. Then you have 2. Then you have 1. Okay. Then here we have to multiply the third row by negative 1. Okay. So in this case, you have 1, 2, 3. Then you have 1 0 0. Then you have 0 1 negative 3. Then you have negative 2 1 0. Then you have 0 0 1. Then you have 5 negative 2 negative 1. Okay. Then in this case, we have to multiply 3 to the third row, then add it to the second row. Again, we have to multiply 3 to the third row, then add it to the second row. And then we have negative 3 times the third row, then add it to the first row. Okay, so again, we have to multiply 3 to the third row, and then add it to the second row. And we also have to multiply negative 3 to the third row, then add it to the first row. So here you have 1 um, 2 0. Then you have negative 14, correct? Then you have 6 3. Then here you have 0 1 0. Then you have 13. Then you have negative 5, then negative 3. Then here you have 0 0 1. Then you have 5, negative 2, then negative 1. Okay, so in this case, we have to multiply negative 2 to the second row, then add it to the first row. Okay, because we have 2 here in the left side. So we have to multiply negative 2 to the second row, then add it to the first row. So you have here, what we have is 1 0 0, then 0, here you have negative 40, 16, 9, then 0 1 0, you have 13, negative 5, negative 3. Then you have 0 0 1, then you have 5, negative 2, negative 1. Okay. So in other words, the inverse, okay, of A is actually, you have negative 40, 16, 9. Then you have 13, negative 5, negative 3. Then you have 5, negative 2, negative. Okay, so often it will not be known in advance if a given n by n matrix A is invertible. However, it is not, if it is not, then by parts of the uh, in the theorem 1.5.3, okay, you have the A and the C, okay, it will be impossible to reduce matrix A to its inverse by elementary row operations. This will be signaled by a row of zeros appearing on the left side of the partition at some stage in the inversion algorithm. So if this occurs, then you will stop the computations and conclude that matrix A is not invertible. Okay, so let's have um, this one. So another example. So you have um, this is actually analyzing homogeneous system. So here determine whether the given homogeneous system is a non-trivial solution. Okay, so for our solution, okay, on the theorem 1.5.3 on parts A and B, a homogeneous linear system that has the trivial solution if and only if its coefficient matrix is invertible. Okay, now on the previous example, the coefficient matrix system is invertible. Okay, as you can see here, okay, this is invertible, and the second is not invertible. Okay, in other words, the system A, this one, it has uh, only one, has only the trivial solution system. Okay, and the other is not. So that's end the presentation for this topic. Thank you very much.